Okay, let us start.
Yes.
Let us start in the second part of the lecture.
Yeah, please. Yeah.
Okay. Let's start the second part of the lecture. Okay, we will start the second part. We will come back again, give more introduction, more analytical introduction. What I do in these lectures is I'm trying to mix between numerics, numbers, and mathematical equations. Because if I concentrate on mathematical equations, guys will get bored. And if I talk about numerics, we will lose the purpose of these lectures. So I always mix between all of them in order to make life easier. Okay, so the idea, if you remember, in quadratic element we have 3 nodes. We have in each element 3 nodes, and we have direction here called eta. Here eta equal +1, and here eta equal -1, and at the middle eta equal to 0. Remember, one time we'll place this node in the quarter point to model fractional mechanics. I will show you how to do this. This is called the quarter point element. Okay, we can do that in finite elements also. Okay, and actually we change any curved element to straight element. This is called natural coordinate or intrinsic coordinates. Okay, this is eta equal +1, eta equal -1, and sometimes you call it xi or zeta or something like that. Is not a problem, the symbol we use. So at these points, displacements are defined here. U at 1, U at 2, these are the nodal values. This could be Ui. This could be Ui, okay? So at any point eta here, at this point we can interpolate actually the value using the nodal values. So we carry out the transformation on I to the phi of I times the value of the nodal displacement. That means phi1 u1 plus phi2 u2 plus phi3 u3. So actually, inside any boundary integral equation, we carry out the integral over the element to the traction ij or something like that between xi and x times the displacement at any point. So if we change the displacement to these points here, when u that u at the nodal values are constant values. So we will end up to this matrix 4. We have that fundamental solution ij or anything times phi1, phi2, phi3 times the displacement at the nodal values. This is in nutshell. This is outline on what we are going to do. So we can arrange this using, we can arrange the H matrix. We can arrange the H matrix when we collocate here, or the source point at the first point, equal to the first u1, u1 at the first node, the second node, the third node. This is u1, and this is u2 for 2D elasticity at the first node, second node, third node. We could have this kind of arrangement based on this matrix 4. We could use this one, but actually this is not the correct arrangement we used to do. What we used to do is to have u1 and u2 at first node, u1 and u2 at the second node, u1 and u2 at the third node. So this is node 1, this is node 2, this is node 3, and we have our H matrix. So this is when we integrate from xi equal 1 to the second element, for example. So it is t11, t12, t21, t22 times here phi1 times phi1 times phi1 times phi1. The same here, but times phi2. The same here, but times phi3, and so on. So this is the arrangement is the most commonly used. Okay, so inside the integral now, the idea is very simple. When we use quadratic variation of displacement, when we use quadratic variation of displacement, the idea is to keep the shape function inside the integral and to get the nodal values outside the integral, because the nodal values are constants. Okay, so the only difference between constant element and the quadratic element, we need to integrate over the element the kernel times the shape function. So if we put this shape function equal to 1, that means we reach a constant element. It's straightforward like this. But now we have a problem. The problem is this kernel is function of the r, of the distant r between the source point and the field point. And the phi is function of eta, is the intrinsic coordinate. So we have mix between r and eta. And we need to change the integral from gamma on the element to the integral between eta equal -1 to eta equal +1. In doing so, we need to change the integrand from f of r to f of eta, or from eta to r, or anything. Plus, don't forget, when we change the coordinate system, we need to multiply by what is called the Jacobian. Okay, when you change the coordinate system from, for example, Cartesian coordinate to polar coordinate, we need to multiply by the Jacobian. The Jacobian in 2D dimensional case, from Cartesian to polar is r. Okay, so we need to multiply by the Jacobian. So we need to compute the Jacobian here. We'll see how to compute this as rules, but bit by bit we'll demonstrate from where these rules comes. This is the first thing. But remember something very good. Remember something very good. This is something off record, okay? When we change from here, when you change from here to here, Jacobian is appeared. That means if we have kind of singularity here, and we find a certain Jacobian to smooth this singularity, for example, if we have here something called like len r, and we have Jacobian here equal r, that means we are going to smooth the singularity. This is the idea of the nonlinear coordinate transformation to compute logarithmic integrals. And some guys, they did it in 1/r integrals. Okay, this is what we call it Terrace transform. Okay, and I will show there is one Chinese guy who did it before Tellis actually, and I will show you the paper now when we come to it. Okay, so coming back, so the main core of quadratic element is we have our matrices. Instead of we have only 2 by 2 single matrix, so we will have 3 of them, and each one is multiplied by the nodal value at the first node, the second node, the third node, and the nodal values are constants. The nodal values are constants. Okay.